So let me start with recalling where we left last time and the problem, and then we will take it from there. So last time we said we had the we basically were in the setting of the Euclid-Selberg trace formula. We generalized a little bit by allowing an arbitrary test function at the Archimedean place. So we said this F infinity was compactly supported smooth function on R plus mod GL2 of R. And then corresponding to this, we had the orbital integral and the discriminant, the regularized orbital integral here, roughly. This was the theta infinity function, which again was not so we had this quantity right here, and I'll tell you why and what these things are in a second. So we are considering, so in this game we always fix a dual group representation. In this case, the dual group is GL2 of C, so I am taking this representation to be this symmetric Arth power representation. That is where this R is coming. So this is R. This is R. This is where this R is coming from. And moreover, this is basically the elliptic part of the trace formula for this specific function at the Archimedean place, so for this general function at the Archimedean place, and at each non-Archimedean place that is not P, I'm choosing the unit element of the Hecke algebra, and at P, I'm choosing the characteristic function of the following set at 2 by 2 matrices with p-adic integer entries such that the determinant of this matrix has p-adic valuation R, and I need to normalize this thing by p to the R by 2. So this is the p piece of this function, and this is supposed to be, well, this is actually giving us the p-th coefficient of the symmetric Arth power L function. So we have this. Let me put a little bit of colors here. But one thing I did not tell you about is the following, and I'm actually surprised that Bill didn't ask this. So this is the elliptic part of the trace formula, but I'm saying that M runs over everything. For instance, if this guy is a square, then the L function doesn't make sense. So actually the elliptic part runs over M such that M squared minus 4p to the R is not a square. So these are Q elliptic elements, by the way, not R elliptic. So there will be R elliptic and R hyperbolic parts of these things, but over the rational numbers, these are Q elliptic. And once again, there's a plus minus sign that I'm ignoring that comes from the determinant. This is like a suitable approximation for our purposes right now. No, this is everything. For each, so this would be the discriminant of the order, and then the orbital integral is asking, like counting how many suborders there are. Good? Okay, so this was where we left, and we said that the discrete part of the trace formula has more than just the cuspidal contribution or the Ramanujan terms. So there are extra terms which I denoted by term of type 1, which was the contribution of the trivial representation, and term of type 2, which already appeared twice today. This was the trivial representation. And this is what came up in Tasha's talk, which was 1/4 trace of this M0 phi rho 0. Is that correct? Or, yeah, I forgot the notation, but this is roughly what it is. So the intertwining operator, the value at 0. So this is the continuous contribution to the discrete part of the trace formula, or rather, the contribution from the continuous spectrum to the discrete part of the trace formula. And one thing about this, so I'll say one word about this, and this is the trivial representation, just the contribution of the trivial representation. Just to tell you why we need to actually take these things out, just to give you a heads up, is the following. So, just a side remark. So these need to be taken out. Because for this sum, either over p or n, if I were to take n, because that's easier to explain, if I were to sum this thing over n, and the contribution of the trivial representation would be roughly of size x to the 3/2, so it is giving a big contribution to this limit, so the limit would not exist unless you take this out. So limit meaning if you divide this by x and take the limit. So we are expecting this whole thing to actually be of size x, but this is x, giving an x to the 3/2 contribution. And moreover, this the type 2 gives a contribution, type 2 of n, let's say, these are all n, is roughly of size x, so this also needs to be taken out. So all I'm saying is it's not just, we're not doing this just for the sports of it, but we're actually, we need to take these guys out. Okay, and the last thing I wrote is what we are looking for. So explicitly what we are looking for is the following. So this first contribution is given as follows: 2 times the sum over p to the r by 2 plus p to the r by 2 minus 1 all the way up to p to the minus r by 2. As this is just the symmetric rth power of the parameter of the identity, trivial representation, plus the integral of this theta infinity function. So this is what we are looking for in this expression. And the second contribution is even more mysterious. It is r plus 1 over 2 times integral of theta infinity of x by square root of x squared minus 1 dx. And here x squared minus 1 should be greater than 0. This is it's an interesting condition. And one should keep in mind, why is this x squared minus 1 coming up all the time in these formulas? It's a reincarnation of the discriminant function, the wild discriminant of GL2. The wild discriminant would be trace squared minus determinant, and over R, if you try to integrate this thing over the trace variable, you can change variables. It basically becomes x squared minus 1. Okay, so great. So what we're going to do is we're going to try to follow what we've done last time. So last time we had 5 steps. We rewrote the trace formula. Well, here it is. It's rewritten, so step 1 is done. Step 2 was an approximate functional equation. I'm going to introduce it here. It will basically be the exact same approximate functional equation with a small twist, which I will explain in a second. And then we do a Poisson summation. Here we see a difference, actually, because last time we had a whole sum over integers. Now we have the sum over this incomplete lattice. Basically what is going on here is, since we are looking at the elliptic part of the trace formula, we're not seeing the hyperbolic terms. So these are the, so to speak, in philosophical sense, these would have been the hyperbolic terms. These would be the split tori. But since in the elliptic part of the trace formula they don't appear, we will need to do something about this, because you can't just sum over an incomplete lattice. Yeah. No, at this point, I'm not even looking at any representation, but in my mind, I'm going to look at the symmetric r plus 1, and that is why I'm putting this p to the r. No, the sum was over this. Yep. No, the sum is over this. So which formula of Zag is? No, the sum is over this. The sum of this is all the possible discriminants. So this is true. LSD for any D is this. Times so this is true. And it still is there. This is the guy. It's just that this D cannot be an Étale algebra. It has to be an actual quadratic extension. Yeah, that's what this is saying. This has nothing to do with that, though. So this is summing over all the possible suborders of the given order with the discriminant, and our order cannot have square discriminant. That's the issue. And that's it. That's what it is. What is the further restriction? That it's like 0 or 1 mod 4? Yep, sure. I mean, this is like d over f squared is this. It has to be that, yeah. But it is in this. It doesn't have anything to do with this. It's incorporated in this L, the definition of the L. The quadratic character is m squared minus 4p to the r, Legendre, basically, divided by f. Okay. So this condition I usually denoted by the dash here. But it's a 2 condition, so usually, I mean, at any finite place, which is not 2, this doesn't say anything. It's vacuous. Okay. But so right now, I mean, I just wrote this thing for a p to the r. I could have as well just set this to be n. It doesn't matter what n is for now. The only issue is if I set this to be n, then this is going to get actually complicated. So I don't want to do that. So let's do it just p to the r. Yeah, otherwise it's a product over divisors of it. Okay, so we're looking for this. We want that. And step 1, as I said, is good. Step 1 was this rewrite, which is fine. Step 2 is approximate functional equation, which is in a second. But let me first talk about step 3 for a second. Step 3 was Poisson summation on the m variable. This is the trace variable. I will talk about what this actually is the special case of, but just to emphasize the problem, this is not a sum over the complete lattice, and it is not that easy to complete this lattice. I cannot just say, all right, I'll just like manually add and subtract the missing terms. Because manually adding and subtracting the missing terms for which this is a square would mean you're adding an L function, a value that is infinity, basically. So one needs to actually do something about it. So we can't just manually complete this sum. What is going to happen is I'm going to introduce the approximate functional equation first to this, which will effectively give a finite sum, and then I'll manually add and subtract the terms. So for that, let's recall the approximate functional equation for this case. So there are 2 cases, which will be basically, depending on if this torus is R anisotropic or R hyperbolic, R split, there will be 2 different, very, very subtly different approximate functional equations. But let me tell you, so let me do the following, how to define this. Okay, I guess this is the easiest way is actually to do this in general. So let me put a lemma here. So let us give ourselves, let D be a discriminant. Well, let me just do this. D be 0 or 1 mod 4. This is what it means. And for all of our things, D will be 0 or 1 mod 4. D will be, for us, m squared minus 4p to the r. Just giving you a heads up. But it's easier to do this. So then L1 d, so this function right here, but as opposed to this, I'm putting a d here, is the following: sum over, this is exactly the same thing that we have done yesterday, 1 over f. This is in the definition of the function. And L equals 1 to infinity, 1 over L, d over f squared over L. And maybe I should put this dash here so that just to emphasize that everything is. And then we have this cutoff functions of yesterday. So there's f, L f squared by square root of m squared minus 4 e to the k. Oh, sorry, square root of d. Plus LF squared over square root of, this is the absolute value of d. Absolute value of d times, there's this h of LF squared over absolute d. Okay, now you're going to tell me this actually looks exactly the same as last time. The difference is as follows. The dual part of this guy actually depends on d, where iota of d will be the following quantity, is d is either 0 or 1, depending on if d is positive or d is negative. Okay? So, iota of 0 or 1. And what does this do? So it does the, basically what is going on is if you have looked at quadratic characters and how their functional equation looks, there's a small twist at the Archimedean factors. For the imaginary quadratic case, you get a gamma factor, which is gamma of z plus 1 over 2, whereas for the real quadratic characters, it's gamma of z over 2. And this iota is basically keeping track of that. So I should tell you what h of d is. So h iota d of y is square root of y divided by 2 pi I, the integral of, this is the vertical integral, gamma of u plus iota d over 2 over gamma of 1 minus u plus iota d over 2 pi y to minus u f tilde of u du. So yesterday iota was 1. Today it can take either values depending on the real characteristic of the torus. So it's neither, it can be 0 or 1. So the reason I'm going over this in detail is the following. It's actually excruciating detail at this point. So it will be very easy to actually get this term, pretty much. We will basically do Poisson sum, and this term will actually occur in the zeroth coefficient. It's just the integral of the function, so this is expected. The problem is how to see this term, which still gives a non-zero contribution to the limits that we are actually interested in, but it doesn't actually show its face anywhere, anywhere at least like seemingly obvious. And one more thing, if you actually look at this very carefully, you would realize that this term does not exist for the Eichler-Salberg trace formula because, so the orbital integrals of the Eichler-Salberg trace formula are supported only on the R-elliptic torus. Whereas this is specifically an integral over the R-hyperbolic torus. So these things were all 0. So this is a very so to speak, R-hyperbolic, R-split specific situation. So it would not occur if you actually limited your test function so that its orbital integral vanished outside of the anisotropic torus. So it is actually then not unreasonable to actually expect that this iota, when iota is 0, would actually play a role, because this is specific to the hyperbolic term. And as you can see over here, when iota is 1, this guy has a pole at u equals -1/2, whereas when iota is 0, this guy has a pole at 0, just to give you a heads up. And this will be very peculiar and particularly important for this isolation of this term in a second. So this is why I'm going over this in such detail. So just in case you guys are like, who cares about this iota? Okay, we have this. All right, now let's set a lemma here. Once we have the approximate functional equation, we basically take this guy, plug it in here, replace the L function with this, as we did yesterday. So step 2 rather, is lemma then the elliptic part can be rewritten as a sum over m such that m squared minus 4p to the r is not a square of this theta infinity m over 2p to the r over 2 times this what we're getting from approximate functional equation. I'll be very brief here because you see it over there. This is m squared minus 4 p to the r by f squared L times the f plus the dual sum. Now, what does this allow us? All right, we did exactly what we have done last time. So we just like had a massive expression. So somehow we had a beautiful expression. We replaced it with this ugly expression, seemingly. But this allows us to do two things. One is, again, if this sum was complete, we could just interchange and do Poisson summation. But moreover, it does the following. I can now add the elements for which this thing is actually a square, because these are now just finite sums, basically. So there's a subtle point here. If this is a square, the approximate functional equation for the zeta function does not look like this. It has an extra term. And so I'm not writing the approximate functional equation for the hyperbolic terms. I'm manually adding and subtracting the terms for which this thing is a square. Does that make sense? Is that like... So I will do the following. I'll write this as this minus what I will call this guy, where sum square will mean sum over m such that m squared minus 4p to the r is a square of the same thing. So I'll just add and subtract, basically. This is a manual, like an ad hoc approach. I'm sure there's a better way of actually handling these terms. This is basically handling the our hyperbolic terms, just manually. There's definitely a better regularization that would actually take care of this in general. But anyway, so we can do this, and we do it. Good. So now this guy is actually over the whole m range. So m is now running over all integers. And we can just do exactly what we have done and do Poisson summation. So we keep that guy. Okay. So step 3 is now within reach. We can do just straightforward Poisson summation on the m sum. M is the trace variable. Once again, I'll emphasize this at the end when we generalize this. So step 3, so Poisson sum. So let's put a lemma here, or a proposition maybe. No. That is that the elliptic part over there is equal to, or rather, let me do this. Elliptic part minus this is equal to sum over, let's do this, p to the r by 2 over 2. This is coming from the relation. So f from 1 to infinity. I'm going to write down basically exactly the same thing that we wrote down yesterday with a little bit, what's that? Elliptic part minus this, plus, is that plus or minus? Sorry, plus, yep. Apologies. So I just wanted to put that guy on the left. 1 over L to 3/2 times the following thing, C in Z. I'll write down a function here, which I will denote by this letter that I don't even know how to pronounce. Well, let's write this as big phi, actually. Times this closed term and sum from yesterday. It's the exact same sum from yesterday. Okay, so where's that? Yeah, there is an f cubed, because yesterday it was f squared times L to the power 3/2. So it's just that. I mean, today I didn't write it in a compact form. I guess like it would have been better if I just wrote it in like LF squared. So all that matters is actually LF squared. So F individually doesn't matter. Yes. This is exactly equal to that. But I didn't tell you what this guy is. Yeah, I'll tell you, and that will be actually M is gone. We did Poisson sum on M. So dual variable is C.
So we go back to the original thesis, and M is a discrete variable.
Sure. What? No. Okay. So the original criticism was the following. So theta is a function on the real line. Great. So I'm only going to do a Poisson sum on theta. Basically, the Fourier transform goes into theta. But in order to do that, what you do is you break your M sum into congruence classes mod LF square for each LF square, where this guy is a constant there. So you take this out. So you just sum over this. So in other words, maybe a simplified, so we have sum over M, theta infinity of M, of a quadratic character, so chi of M, right? A discriminant, say, like D. Then you can do the following. You break this M sum into A mod D. For each A, now chi is constant, right? So you do chi of A. But you still have the sum over M, now congruent to A mod D, right? Theta infinity of M. Now this is a perfectly legal, valid Poisson summation, because you could write this as literally just, right? So this is what I'm doing. Oh, sorry. Yes, P to the R. Yes, absolutely. I forgot that. Yes, this is P to the R. Yeah, there's no N. N was P to the R. I mean, my notes are just a little bit messy here. Okay, any other question? Just please stop and ask, because it will get technical. Because I want to actually show where this guy appears for once. Okay, so this is the lemma. Elliptic part is this. All right, now step 4 was the analysis of the C equals 0 term, the dominant term. But before the analysis, let me actually tell you what this big phi hat function is. Okay, where this phi hat of C P to the R, comma L, comma F is the following gadget. So this is a Fourier transform, basically, of this theta. But we have this f function as we had yesterday, LF squared times 4p to the r to the 1/2 over square root of, let's do x squared minus 1 plus LF squared times 4p to the r 1/2. This is exactly the same, these are minus 1/2, sorry. Exactly the same function that we wrote down yesterday. I'm just writing it down to emphasize one point. So h of this LF squared 4p to the r over minus 1/2 x squared minus 1 times the exponential e to the minus xc p to the r by 2 by 2lf squared dx. So the only difference is basically there will be an iota here, which will depend on actually p and where we are summing over. Basically, if x squared minus 1 is bigger than 0, then we will take iota to be 0. If x squared minus 1 is smaller than 0, iota will be, so maybe iota of x is the right way to put it, where iota of x will be 0 or 1, depending on if x squared minus 1 is less than, it's greater than 0, and x squared minus 1 is less than 0. So this is a reflection of this fact that on the R elliptic torus, the approximate functional equation looks a little bit different than how it looks like on the R hyperbolic torus. Okay. So the thing to keep in mind from this formula is the following. For iota equals 0, this is yesterday's situation. And iota equals 0, we have an extra, we have a new phenomenon. And the formula right here, I'll bug you with this formula for about 10 more minutes until we actually get to this point. But basically what's going to happen is we're going to try to understand the contribution, this is sum when c equals 0, and especially when this iota of x is actually 0. And that will actually contribute, that will give a contribution to this guy and that guy. And that will be the aim for the next 10 to 15 minutes. Okay, so this completes the step number 3, basically. Step number 4 is the dominant term. So the dominant term is supposed to give us some information about this discrete contributions which are not cuspidal, which are not tempered in general. So step number 4 is what is the contribution of the C0 term. Let me remind you what happened last time, yesterday, when we analyzed this contribution. We analyzed these two F part and the H part separately, and the F part had given us a contribution of the following form. So F part was giving us an x to the 3/2 times an integral from yesterday. So this is yesterday. dx. And then there was a term which got canceled with the H part, so I'm not going to write it down. And the H part had given us a contribution for actually the extra, which canceled with the hyperbolic term. So it gave us a contribution of the form like pi of zeta of 0 times x times some stuff. Okay. So we're going to see a little bit of, but this was actually summed over n. So sum over n, sum over n, fn. So today, I'm not going to sum over n. I will just look at one term at a time. So I'm fixing my n to be p to the r, and I'm looking at one term at a time. Okay, so here is what's going to happen, and I'm going to first state this as a lemma, and then I'll go over some of the ideas in the proof. Here's a theorem. So this c equals 0 term is equal to the trace of trivial representation maybe let me just call it f minus the trace of, well, called it, this is a bad notation, the contribution number 2, okay, plus something very explicit, which I'm not going to write down because it would take the whole board. In other words, these two guys, they both actually appear in the c equals 0 term. So now how does that work? The whole idea, I mean, I guess, so the number 2 term is this. Number 1 term is this trace of 1 of f is this. Now the question is, how do you actually get any of this, and where are these, like heuristically, where are these terms coming from? So trace of 1 is easy to explain because it's just the integral of the function. So how do you get the integral of the function? You literally just calculate this. The main term will actually be coming from the following. So the whole proof of that theorem depends on expressing f as its Melon transform, its inverse Melon transform, calculating a certain Dirichlet series, and shifting contours. So if you're planning on falling asleep, right now is the time. I'll wake you up in 15 minutes. So, sketch of the proof. I mean, I want to do this because, well, it is good. Like, there's no way to avoid dirty work sometimes. You got to do it. You got to do what you got to do. Okay, so the idea is contour shifts, but like, how do we get to contour shifts to start with? So let's do it slowly, step by step. So the idea is, or method, is Melon transform, Melon inversion, plus contour shifting. And this is very standard, actually, for certain type of analytic problems. You just write down a generating series by Melon inversion. You write it as a Melon transform of its, or Melon inverse of its generating function, and then you try to understand what's going on with the series just by looking at the function itself. Okay, so let's start with Melon inversion. Number 1, Melon inversion. What does Melon inversion give? So I'm going to do the part for f, because h is a little bit more detailed. For f, so f of Lf squared times 4p to the k of p to the r to minus 1/2 over square root of 1 minus x squared. So you can write this as the Melon inverse of the Melon transform of f times whatever is inside comes in as the variable. So Lf squared times 4p to the r to the minus 1/2 over, what's that? Square root of 1 minus x squared times, what's that? Where's my u? Minus u, I believe, times du. Okay. So basically what this does is the following. Now I can bring the rest of the sum in and sum over L and F, because L and F are now outside of the function f. This is the whole reason why I use Melon inversion. So this L and F was inside f. By Melon inverse, this is now just Lf squared to minus u. So I'll just bring this L and F sum and just try to sum this whole thing up. Okay. So then, so this is number 1. Number 2, if we bring the L and F sum in, what we're looking at is a sum over f from 1 to infinity and a sum over L, so let me just do F and L at the same time, of 1 over f to the 1 plus 2 times u plus 1. That is coming from f squared to minus u here, and f cubed was over there, times maybe sum over L from 1 to infinity, 1 over L to the u plus 1, times this closed term and sum. Square root of L. Okay, so now this is great. I mean, we have an R and U and everything. And by the way, this whole thing, so this is the L and F part, and note that what I'm trying to understand is what happens to this. So I'm going to try to shift this contour to the left. So I'm trying to go as far left as possible because for beyond endoscopy purposes, I'm going to be summing over P. The exponent of P matters. So I'm trying to make the exponent of P as small as possible. So I'm going to shift the contour to left. Okay? But in order to do that, I need to understand what this function looks like. Where are the poles where are the poles of this function? This is the whole game, because this depends on u. I know that f tilde has a pole at u equals 0. So if there is nothing, so this is at 1, if there's nothing in between, I can go all the way down to the left. But there may be something. Or maybe this is something big, say like 10. We're going to go all the way to the left. Okay, here, now we have a very nice lemma. The lemma goes as follows. The lemma basically says that you can calculate this guy. So lemma, which I didn't have time to explain yesterday, this also goes back to yesterday's results as well. So one actually needed to calculate this. I didn't tell you, I didn't show you yesterday, but in order to actually get all of those main term contributions, one actually needed to calculate this. And, well, this guy is 4 times zeta of 2 times u plus 1 over zeta of u plus 2 times, believe it or not, the following quantity, p to the r over 2 plus p to the r over 2 minus 1 plus p to the minus r over 2. So this is what this guy is. Isn't it amazing? So as you can see, I mean, we're already seeing a term right here, what we were looking for. Right here. Oh, there's a u here. That u times all of these. So when u equals 1, we're going to get this term. Okay. I believe this is true. I hope this is true. Wait. Did I do this? Minus. Let me just write this thing down explicitly as a compact form that's easier to manage. It is 1 minus p to the minus u times r plus 1 over 1 minus p to the minus u. So this is what it is. That's a better idea too. Okay. Good. Okay, so far so good. So we have an explicit expression for what's going to go in here. Then we basically stare at this and try to understand where the poles are. And the poles are going to be u equals minus a half, I believe. And at minus a half, we are getting half, yeah. U equals minus a half. Zeta is going to give a pole. This guy doesn't have a pole. So the only zeros are going to start happening after u equals minus 1, if you like. Or, well, if you assume Riemann, this will only have zeros at u equals minus 3 half. So we can go all the way down to 3 half. So basically, the game becomes, can we shift this contour all the way to the left? And you can. And the poles, the contributions are going to be u equals 0 and minus a half. And then one basically does the exact same thing here for the contribution of h of x. So does this make sense? A little bit the sketch. So basic idea, use Melon Inversion, bring the L and F sum in, calculate, and look at the poles of the generating series. You plug this guy in, so FU times this. And you look at the poles of this guy. So I want to shift contours for the following reasons. So two things. One, I want to eventually sum this thing over p to the k, right? So if I can show that this sum is small, this term is small as a function of p, then I can show that this would not contribute to beyond endoscopy limit. And look at this. Now, how does this p appear? What is a p dependence on this sum? So p appears as basically p to the r over 2 times u. So as long as the real part of u is negative, for instance, this p will appear with negative exponents. So if you sum, this is not going to contribute to the limit. So this is the whole idea of shifting the contour to the left. And basically how much you can shift is dictated by the poles of whatever generating series is involved. Yeah, so in the contour is somewhere all the way to the right now, because so that I could write down the sum, because otherwise, like, it wouldn't converge. Like, this shift, the interchange of integral and the sum would not make sense. And then I'm going all the way to the back to try to, like, pick up everything. Because in order to write that Dirichlet series, I'm interchanging this f sum with that contour. So the double integral, so to speak, or in this case triple, should converge absolutely. To guarantee that, I start very right. So the contour starts here at 10, say, and then I go all the way down as far as I can go. Oh, I would like to go all the way down to infinity, but I can't because, like, there are zeros of this guy. So, I mean, optimally, I'd like to go to u to the minus 3/2. U equals minus 3/2. Well, I mean, if you assume Riemann, you can. Because the only possibility is going to come from here. You don't like that. Well, I mean, we're doing beyond endoscopy. I don't know which one is harder, Riemann or beyond endoscopy. You're not responding. Anyways, so for all this, actually, going slightly to the left of 1 minus 1/2 is fine. So this guy actually converges absolutely. So it's all good. I will actually shift everything to u equals minus 1/2. I'll stop there. There will be a principal value. So everything goes to u equals minus 1/2. Okay, so if anybody had fallen asleep, wake up. This was the pain. So now this, as you can imagine, this part will contribute to the trivial representation right here. Well, of course, the trivial representation will actually get an extra contribution from the other term as well, but basically it will be set in stone by analyzing these Dirichlet series. But where is this guy coming from? Because this has nothing to do with that. Well, basically what is happening is, when you look at this H and do the exact same calculation, the Dirichlet series that you're going to get, because of the small iota shift, would be this. And then you'll be getting this guy, which is weighted by certain gamma factors. And then the whole game basically becomes, look at the product of this guy with the gamma factors and analyze each pole. One of the poles, well, okay, one of the poles has residue this guy somehow. Like, you need to actually calculate this. This is a calculation, but this corresponds to the same analysis on H of basically like H attached to the R hyperbolic torus. So it is very easy to explain, like, by waving hands. You do the exact same calculation and calculate the poles. It would be almost impossible to actually go over this in 2 lectures, because one needs to analyze not just this, but bring in the hyperbolic terms and the gamma factors, and basically analyze like every single pole that is attached, there are 3 of them. 2 of them doesn't matter. 1 of them gives this contribution. If anybody is interested in the details, just come find me in like 10 minutes. I just want to move on a little bit because this will be, well, I'd like to leave the details of this at this stage and basically move on to a comparison with what Langlands, Frankel, and Nigaud did. And in order to do that, I need to introduce what Langlands, Nigaud, and Frankel did. So this is roughly the step 4 contribution. The upshot of the whole story is the following. The contribution of both the trivial representation and the continuous contribution to the discrete part of the trace formula are captured in this C equals 0, the dominant term. Both of them appear in the setting in the dominant term. Is there any questions so far? At least the upshot should be should make a little bit of sense. Yep. So the very explicit term is, as I said, you shift the contour to u equals -1/2. That's that contour integral. Because you can now move further down than 1/2 because of these unnecessary terms. I'm almost certain that these are just byproducts of some analytic issue, but I mean, at the moment they are. Usually in this kind of game, what you would expect is to get the main term and be able to shift the contour all the way to -infinity. But unfortunately, we have this zeta. If this zeta was not there, we could be able to shift all the way to -infinity. Any other question? Okay, so now one question you may ask is what happened to step 5? Well, step 5 is hard for symmetric kth power, symmetric rth power. If we could do step 5 for symmetric rth power, we would basically roughly prove Ramanujan conjecture for GL2, for every R. Or any, like R that goes to infinity would actually essentially do it. So step 5 is open. 5 is open. For R equals 1 and 2, there is, I mean, R equals 1 was yesterday's case, so one can do it. R equals 2 can be done with basically the same methods. For anything more than 2 is, so this is okay, let's say. But, I mean, okay, but like 1 is written, 2 is not written. Greater than or equal to 3 is just a complete question mark. That's like symmetric third power and above for is completely open. All right. So in the last remaining part, so maybe I should tell you what's going to happen next. I'm going to introduce what Frankel, Langlands, and Nigaud did, because they also took this problem of isolating the contribution of the trivial representation. Not this guy, just that. And they did something which quite often is maybe somehow, I shouldn't say misunderstood, but not explained usually. So I want to explain, and I want to compare this approach to that and what it gives and what it doesn't give. Because their result is actually far more general than GL2. They start with an arbitrary semisimple group. Simply connected, I guess. But their method can be, I mean, it just works for essentially any group. Okay. So from now on, there will be 2 aims. One will be to describe what the paper of Langlands, Frankel, and Nigaud, roughly. So Frankel, Langlands, and Nigaud's approach. So what is the approach? So the approach to understanding the contribution of the trivial representation to the geometric side of the trace formula. So maybe I should state this as problem. So the problem that they tackled is exactly what we have been saying. Isolate trace of 1 of f. This is the problem that they actually tackled. But their situation is they're taking a pretty much arbitrary g, but for reasons to follow, they take g to be semi-simple and, derived groups simply connected. So that is what they actually take. Other than that, they don't really have much of a restriction. And even this is not that important. So what they do is they actually isolate this trace in, pretty much similar, at least in spirit, method. They use a Poisson summation on a certain space, on the orbital integrals, and they basically isolate the trace of, what do we do over here? We isolate it. We basically showed that a certain term in the geometric side, a certain sum, corresponds to the trace. You know, the trace of the trivial representation is a spectral term, so we're basically trying to understand it in terms of geometric terms. So it's actually close to what Tasha was doing in spirit, like in stabilizing the trace formula. Like there's some sort of an interaction between the spectral terms and the non-tempered spectral terms and geometric terms, and we're trying to understand this guy. Oh, I understand now. In the geometric set, that's what I mean. Sorry. Yeah. And in particular, what they do is they actually understand, they take the elliptic part of the trace formula. Okay, so in the last 3 minutes, let me give you a rough idea of what they do. So the idea, or rough outline, so roughly, what they do is their main observation is that, it's not their, maybe there. So semi-simple conjugacy classes are parametrized by what is called the Steinberg-Hitchin base, which appeared in Julia's talk, and I should also make a difference. They're not just semi-simple conjugacy class, semi-simple stable conjugacy classes. So they basically start life with the stable trace formula. And why is this any useful? The usefulness is because of the following observation. The Steinberg-Hitchin class, which is an enhanced version of the space of characteristic polynomials, is almost an affine space. So why is this any useful? Why may this be any useful? So this Steinberg-Hitchin base is almost an affine space. And examples, SLN or GLN, doesn't matter. This is the space of characteristic polynomials. Or SLN, space of characteristic polynomials with constant term 1. So, as you see, this is just a n-1 times a gm factor. And here, this is just a n-1. And in general, there's a general construction that Julia introduced. This basically looks like an affine space. So the idea that they had was to use Poisson summation on the space. But in order to do that, one needs to actually take this stable trace formula, rewrite it as a sum over here, because these variables are going to appear, and then basically do a Poisson sum over this space. And secretly, or not so secretly, we have been doing the exact same thing in the special case of GL2. In GL2, this is just A1 times GM, and we were fixing the GM part for all that matters, because this P to the R was the GM part. And once we fixed that, we did a Poisson sum over this M variable, which kept coming up and up and up, and that is just trace variable. So we were doing this in more like hands-on approach, just doing it elementarily, so to speak. What these guys are going to try to do is to adelically write down the stable trace formula over the space and try to do a Poisson sum adelically over this. So in the second lecture, I'm going to describe this and what goes wrong and what goes right. I didn't understand. Oh, but so here is what is going on. So on the spectral side, we have a sum over cusp plus trace of 1, right? So if you can write this as space, like some c equals not 0 plus trivial minus this trace of c of f plus something explicit. Basically, you just don't take any of these guys, so these two guys get canceled. Uh-huh. No, I am just trying to isolate this on the geometric side so that I'm not going to even consider this term. Remember, yesterday when we were actually doing the Poisson sum, there was an extra term that was coming up, which was x to the 3/2 times this integral, right? And I said I had a lemma which said that this integral is 0. Normally, what you would do is to basically not even consider this integral because this is the contribution of the trivial representation. And that is what we isolated over here. I guess it does come out to be cancellation. You could just put it on the other side and.
So, what is the minimum you have to shift before you discover
the minimum that I have to shift? So the truth is actually p to the r over 2. So u equals 1, I believe, so u equals minus 1. This is the pole of this guy is actually, maybe this, but one of these guys actually have a pole at 1. Well, I'm trying to shift actually as far as I can go, but minus a half seems to be where things stop at this point. Because there's also a little bit of maybe I'll tell you in a little bit. It's a little detail.